In the last lecture, we had introduced the concepts of discrete integral transforms and extended our ideas to define what we called as the quantum Fourier transform. Just to recollect what we did last time is to say that suppose I have a function fx of discrete variable x, which belongs to, as we defined, Sn, which is a collection of numbers 0, 1, 2, etc. up to n minus 1. We defined a discrete integral transform of this function to be given by f tilde of y equal to sum over x equal to 0 to n minus 1 of a kernel which we wrote as k yx times f of x. And we said that in case this k is invertible, or in our particular case of interest, if k is unitary, we can define inverse integral transform, which will be given as fx equal to sum over y equal to 0 to n minus 1, k dagger of xy and f tilde of y. Now, the way we defined a Fourier transform was to take a specific case of this kernel. But before that, what we did is to say that this definition enables us to generalize it or extend it to the case of a basis state. Now, so what we did is the following. We said that supposing I have a basis, set of basis states, let us say computational basis, then supposing u acts on one of those computational basis, u is a unitary operator, then by definition of a unitary operator, this will give me a linear combination with matrix element of u in the states xy, y. Now, what we said is this: compare this with the expression of sum over y, kxy, y. This tells me that I can essentially compute the Fourier transform of a basis in a similar way, provided the matrix elements of the unitary operator that I write down can be identified with the kernel that we talked about earlier. Now, this has a great advantage in the sense that if we did it, it would mean that I can calculate the discrete integral transform of all the members of a basis set in one go. And this is, of course, as we have seen several times, is because of the quantum parallelism that is inherent in any quantum computation. So, what we said is this, that supposing I took this kxy to be given by 1 over square root of n e to the power 2 pi I xy divided by n, which is nothing but 1 over square root of n, the nth root of unity, which is represented by omega n raised to the power xy. This defines a Fourier transform. And we will call it simply QFT. The essential idea is the following, that what we are doing is basically very similar to the way one calculates Fourier transform for a real or a complex variables in our mathematical analysis, excepting that our variables are discrete and we have been able to extend it from the case of functions to the case of basis states. Now with this recapitulation of what we did last time, let me now continue with Fourier transform. Now one of the applications that we will be making will be to find a period. So let me define what is meant by it, but before I do that, let me remind you that what we want to do ultimately is to get a factorization algorithm in place, which was due to Shor. And what we are doing in the last and next couple of lectures is to get the components of Shor's algorithm in place. One of the essential points of the Shor's factorization algorithm is to find the period of a function, and this using a quantum Fourier transform circuit. Now as is normally done, a function is said to be periodic if f of x plus p is equal to f of x. We are familiar with several periodic functions. For example, trigonometric functions of the type of sine, cosines are periodic functions with period 2 pi, after which they are all repeated. The thing that we are talking about here is, because our variables are discrete variables, we are saying that p is a number, p is a period. So p is the period after which the value of the function gets repeated. So p is a discrete number in this particular case, and this is called periodicity. As with all quantum algorithms, we will have an oracle which will calculate such a function and output it to the target. And as we know that if we had set our target register or the ancilla initially to 0, then of course the f of x is calculated corresponding to all the different x in the input, and I get simultaneously a linear combination of f of x corresponding to every x. So let us see how does it work. What I am going to do, however, instead of doing it purely formally for an arbitrary periodic function, let me illustrate it for the case of 2 and 3 qubits. In this particular case, I am first taking a 3 qubit case and try to find out what does this period mean and how is Fourier transform going to help us. So let me illustrate this for a 3 qubits case. So the first thing that we do is to let the input register contain a uniform linear combination of the 3 qubit basis state. Now what it means is, my first register, which is my input register, will contain then 1 over square root of 8, 0, 0, 0, 3 qubit case, 0, 0, 1. I will just write down, though there are several terms in it, but it is not impossible to write all of them down. Now instead of carrying on this 3 qubits, which also is a bit clumsy, we will go over to the decimal representation and write this simply as 0 plus 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7. And as we have said, my target register, the second register, is set to 0, 0, 0, which is identical to 0 in the 3 qubit notation. We have several times pointed out the way to get the first register in this place is to start with this 0, 0, 0 and then pass each qubit through a Hadamard gate, so that we get a linear combination of the various states in 3 qubit basis. The oracle that we have, I am not reproducing that picture again, this is routine, I have done it several times, but what the oracle does is to compute f of x. And since my second register was set to null, the output of the second register will contain f of x. Obviously, I will not be able to write the output in a factored form because the output gets entangled. Let me do this, write this output as psi, which is given by uf, that is my unitary operator acting on the input state, which was 1 over square root of 8 sum over x equal to 0 to 7, x 0, this was my input, and my output is then on when uf acts on this. So this is x equal to 0 to 7, x and fx. So the output is entangled. Since I have just 8 terms, it will help me if we just write this down. So we will write down psi is equal to 1 over square root of 8, 0 f0, I am writing it in both the states together instead of factored form, plus 1 f1 like this, so there are 8 terms in it. So this is what my oracle has given us. So this uf is the oracle which computes the function. Let me write this clearly because there will be one more uf that I will be talking about. Now at this stage what I will do is, I will apply QFT, quantum Fourier transform, on the first register. Now of course we will see later in this lecture that corresponding to quantum Fourier transform I can find a unitary operator which will do this job, but let us just assume that this is so and proceed. Notice one thing, if QFT is applied on the first register, since it is a 3 qubit QFT, each term gives me 8 terms. Since I already have 8 terms, when I apply QFT, I will get 8 into 8 equal to 64 terms. Now obviously, I am not planning to write all of them down, but I would like you to have a feel of what these 64 terms, how can they be grouped together and things like that. So QFT on psi. Let us call it psi ft prime, psi prime. So psi prime then is given by, I already had a 1 over square root of 8 in my definition of the input, and this QFT gives me another square root of 8. So I get 1 over 8 sum over x equal to 0 to 7, sum over y equal to 0 to 7, e to the power 2 pi I xy divided by 8 y f x. Notice I left the second register untouched, but applied the Fourier transform on the first register. So first register we had x f x. So this now each x gave me 8 terms and I am left with 64 terms. Now though I have 64 terms, what I am going to do is to group them, and I will group them in the following way. For each I will group 8 terms corresponding to each value of y. So let me just show you how this will be done. So let me rewrite psi prime. So I have a 1 over 8. Now supposing y is equal to 0 in this, then what do I have here? Now if y equal to 0, this exponential calculation is easy irrespective of what is the value of your x. So each one, the exponential to the power anything where there is a 0, that is equal to 1. So therefore, since y is equal to 0, my sum is over 1 to 7. So therefore, what I get here is f0 plus f1 up to f7. I will write down one more term. When y is equal to 1, remember that the y is being factored out, so I will have only x varying from 0 to 7. So here y is being put equal to 1. So I will get the first term still equal to f0, because if x is equal to 0, e to the power 0 is equal to 1. But now I will start having this exponential factor. I have y is equal to 1, so I get 2 pi I x is equal to 1, y equal to 1 divided by 8 f1 plus e to the power next time my x is equal to 2, so I get 4 pi I y is equal to 1 by 8 f2 etc etc, and the last term will obviously be e to the power 7 into 2 pi I divided by 8 f7. It is impractical to write down the remaining terms, so I will just put dot dot dot, but let us look at the last term also, which is this. So what you do here is to put the value of y is equal to 7, x goes from 0 to 7 again, so therefore I get f of 0. This is just a matter of multiplication, e to the power 14 pi I by 8 f1 plus etc etc e to the power 14 pi I multiplied by 7 by 8 f7. Now notice that I have so far not utilized the property that I started with, namely what I have is a periodic function. So once we have grouped these 64 terms in terms of what is the coefficient with which comes for y equal to 0, y equal to 1 up to y equal to 7, what we will show now is that if you assume a period, in this example I will take the period to be equal to 2. If you assume a period, many of the terms will vanish, leaving you with certain terms which depend upon what the assumed value of period is. So let us assume the period to be equal to 2, so that I take x plus p, the function of x plus p is equal to f of x, and I will take p to be equal to 2. Now if you take p to be equal to 2, then I have f0 equal to f2 equal to f4 equal to f6 equal to A, and f1 equal to f3 equal to f5 equal to f7 equal to B. Now out of these, the first term is much easier to understand, because the first term, which corresponds to y equal to 0. So what I have is 1 over 8, 0 multiplied by, remember this was f0 plus f1 up to f7. But we have said f0 is equal to f2 equal to f4 equal to f6. So therefore, these are states. So this gives you simply 1 over 8, 0 and 4 times state A plus 4 times state B. That's fairly straightforward and trivial. Now let us look at what do I get for the state 1. For the state 1, what I get is this, 1 over 8 again. This is state 1. Remember, I have f0, f2, f4 and f6 are the same. So therefore, I put all of them together A into 1 plus e to the power 2 into 2 pi I by 8 plus e to the power 4 into 2 pi I by 8 plus e to the power 6 into 2 pi I by 8 plus B into e to the power 1 into 2 pi I by 8. Just write it in a symmetric fashion. E to the power 3 into 2 pi I by 8 plus e to the power 5 into 2 pi I by 8 and finally e to the power 7 into 2 pi I. Now let us look at what do I have here. For the coefficient of A, what I have is 1 plus, this is e to the power pi I by 4. So I get e to the power pi I by 2. Then plus e to the power, this is 4 into 2, so e to the power pi I plus e to the power, this is 12 pi I by 8. So what do I actually get here? So this is equal to 1 plus e to the power pi I by 2, so which is cos pi by 2 plus I sin pi by 2, so which is equal to 1 plus I. Now this is e to the power pi I, which is cos pi, which is minus 1, plus I sin pi, which is 0, so minus 1, plus e to the power 12 pi I by 8, which is 3 by 2 pi I, which will simply give you minus I. So this adds up to 0. Now likewise, you can do the coefficient for the state B. Now look at what do I get there. I have e to the power pi I by 4 here. So this is cos pi by 4 plus I sin pi by 4, which is nothing but 1 plus I by root 2. Do the next term, you get minus 1 plus I by root 2, because it is simply 3 pi I by 4. You have to just be careful on which quadrant you are to find out the cosine and the sine value properly. So minus 1 minus I by root 2 and plus 1 minus I by root 2, which is equal to 0. Number of i's will be equal to the number of I minus i's, and so on and so forth. And likewise you can show that all other terms are also 0, but that is not true of the state which is the coefficient of 4. So in the coefficient of 4, what I get is 1 over 8. Supposing I am just collecting the terms for A. So I get e to the power 4 into 0 into 2 pi I by 8. This 0, 2, 4, 6, they will be running because they are the value of x that comes up. So plus e to the power 4, this 4 came from this 4, into 2 into 2 pi I by 8, plus e to the power 6 into 2 into 2 pi I by 8, sorry, 4 into 4 into 2 pi I by 8, plus e to the power 4 into 6 into 2 pi I by 8. And likewise for B. So it is 1 over 8 A into. Now notice this term is of course 1 because it is 0. What about this term? This is e to the power 16 pi I by 8, which is e to the power 2 pi I by 8, but then both cos and sin have a periodicity of 2 pi. So each one of these terms is equal to 1. So this is 4. Similarly, collect the terms for B. I have given the details in the slide, and you will find that each one of the terms happens to be equal to minus 1, because the first term there is e to the power 4 into 1 into 2 pi I by 8, which is e to the power 8 pi I by 8, which is e to the power pi I cos pi plus I sin pi I. This works out to minus 1. Of course, you can check that each one of the terms will turn out to be minus 1, and this will be minus 4. But this overall sign is totally immaterial. So what I get when I do this is given in this slide, that I have for y equal to 0, I get half because there was a 1 by 8 outside, a plus b, and the other one is 4 into a minus b. So if I now measure the first register, so if I get either 0 or 4, I can conclude that my periodicity was 2.